The following reaction occurs in an aqueous solution, and you have HgCl4 2 minus plus Cu2 plus, which is the copper ion, turning into CuCl4 2 minus plus Hg2 plus. Hg is your mercury, by the way, and the KEQ of that is 4.55 by 10 to the minus 11. And then they tell you that a solution containing a mixture of HgCl4 and Cu2 plus ions is prepared. The initial concentration of each ion is 0.1 mole per liter, and there are no other ions present. And they ask you to calculate the concentration of Hg ions once the system has reached equilibrium. Okay, so when you are doing equilibrium questions, calculation questions for module 5, there are a few things that you need. You need to know the actual K value, this one here. Okay, so the question has to give you that. And you also need to know what equation you're working with. Okay, so those are the two things you need to look out for a module 5 calculation question. The K value and the equation that goes with it. What you do from getting that equation is you need to know what the equilibrium expression is that corresponds to this number. Okay, so what you've learned at school is that your equilibrium expression is the concentration of the products divided by the concentration of your reactants. Yeah, and if there's any coefficients out the front, then that gets raised to the power, right?
Mhm.
So what's the equilibrium expression for this equation? Yeah, so that's going to be my expression. And now, when they tell you that there's something that they added in and then it reaches equilibrium over time, you need to set up your ice table to figure out the concentrations over time. So your ice table is tracking your concentrations of the stuff that's in your system. So the purpose of the ice table is to keep track of the concentrations inside of your beaker, okay?
Mhm.
For pure solids and for pure liquids, the concentrations are assumed to not change, which is why they don't show up on your equilibrium expression. But in this case, everything is aqueous, which is not a pure liquid, so it does go on my ice table. So my ice table is ICE. I stands for initial concentration. That's what you have at the very start of your system. Yeah, so that's what the scientists initially put into the beaker to get it to react. Change is the C is the change. C is the change in concentration. The way a system moves depends on Le Chatelier's principle. So if it moves to the right, then the right is going to be plus as the change because it's shifting that way, and it'll be minus for the other thing. And the other thing to consider is that the change depends on your stoichiometric ratio, okay, which means the number out the front of your formula in your equation. So the change is depending on my ratio. That's the numbers in front of my formulas in my equation. And then equilibrium is when I add my initial and my change together. And equilibrium is what I put into my equilibrium expression over here.
Mhm.
So my initials, they've told me, of each ion is 0.1 molar of my HgCl4 and my Cu2 plus. Okay, the fact that they've already given me concentration means that I can pop it straight in, but be careful. If a question gives you moles and they've told you volume separately, then you need to calculate the volume, yeah? And if they've actually given you grams and they say, oh, I dissolved this, I don't know, 5 grams in this amount of volume, then you need to do mass divided by molar mass to get the moles first and then divided by the volume afterwards. So in this case, it's already in terms of concentration. So that's just going to be 0.1 for HgCl4 and 0.1 for Cu2 plus. If they haven't given you the concentration of anything else at the start, that probably means they didn't add it in and the concentration would just be 0. So according to Le Chatelier's principle, if I don't have something in my system, I'm going to shift that way to make it, right? So if the concentration is 0, I'm going to shift to that way to try to bring it back up. So I'm going to shift that way. So that's my equation, which means I don't know what that shift is. So that's what I'm looking for, okay? If I don't know what that shift is, I'm just going to give it an unknown letter x that I'm looking for. So because I'm shifting to the right, it's going to be plus x and plus x. And the reason it's plus x is because the coefficients is all 1. But let's say, for example, it was 2Hg2 plus, then that would be plus 2x. So it's going to be plus x, which means the thing that you multiply x by, look at your coefficient. If it's 3 at the front, then it's going to be plus 3x for that thing. Okay. And then same thing for the others as well. If it's like 2 here, but I'm shifting away from it, then it would be minus 2x. But in this case, it's just a 1. So it's going to be minus x here and minus x here. So that's how I know what my changes are. And then my equilibrium is my initial plus my change. Okay, so whatever is in the I box and whatever is in the C box, I combine that together to get my E. So that's going to be 0.1 minus x. That's going to be 0.1 minus x. This is going to be x, and this is going to be x. Okay. So then now that I've got my equilibrium concentrations, that's the goal of the ICE table, by the way. You want to get expressions that you can work with, that you can substitute back into your fraction, yeah? So I'm going to sub everything back in, and it's okay that I don't know it because that's what I'm looking for. So I have x and x up the top, so that's going to be x squared. And I have 0.1 minus x and 0.1 minus x down the bottom. So that's going to be 0.1 minus x squared, yeah? So that whole thing is equal to 4.55 by 10 to the minus 11. Now, if you end up with a quadratic that you have to solve, normally it's really easy to just say that something's approximately 0 so that you can get rid of it and not do the quadratic. However, in this case, you don't have to do that because the power of 2 is on the top as well as on the bottom. So because the power of 2 is on the top and on the bottom, what I can actually do is square root everything to get rid of the power. So I don't need to assume that it's 0 or anything. So what I'm going to do is I'm going to square root the top, I'm going to square root the bottom. So what I end up with left is x on 0.1 minus x is my square root 4.55 by 10 to the minus 11. Yeah?
Yeah.
So what number do you get when you square root this? So I'm just going to do that number now so that I can simplify my number. So when you do square root 4.55 by 10 to the minus 11 in your calculator, what number do you get? And then all I need to do now is just some maths so that I can figure out my x. So I'm going to move my 0.1 minus x over. So that gives me x is equal to 6.74 by 10 to the minus 6.1 minus x. So when I expand this bracket out, I get 6.74 times 10 to the minus 7 because I multiplied it by 0.1, yeah? So since it's multiplied by 0.1, it becomes 10 to the minus 7 instead of 10 to the minus 6. And then the other thing that I have is my number multiplied by my x. So that becomes minus 6.74 by 10 to the minus 6x. And then for me to figure out x, I need to group all of the x's together. So this goes over here. So that's 1 plus 6.74 by 10 to the minus 6 x is equal to 6.74 by 10 to the minus 7. So this is just me doing maths, trying to group my x together. So then last thing I have to do is divide this over. So then x ends up being 6.74 by 10 to the minus 7, all on 1 plus 6.74 by 10 to the minus 6. Now, the reason why it gives you about the same answer is because 6.74 by 10 to the minus 6 is really small, yeah? So because it's really small, it's technically about 0. You can just say it's 0. So then what you end up with is actually just this, 6.74 by 10 to the minus 7 divided by 1. So this would just end up being 6.74 by 10 to the minus 7. Okay, so then that's my x value, yeah? Now, what I have to go back to is have a look at what the question's asking me for. It's asking me for the concentration of Hg2 plus ions. So I need to see what X corresponds to. So over here, backed up to my ice table, X is the concentration of Hg2 plus and CuCl4 minus. So going back up to the table, I realized that X is already in the column for Hg2 plus, so that's already the concentration of Hg2 plus. So this answer up here, this 6.74 by 10 to the minus 7 molar, that's the concentration of Hg2 plus that I'm looking for.